Welcome to week 8 for CIT-145 programming in C. This week we are going to be discussing pointers in C. So pointers are essentially, they hold value, but they hold value by pointing to memory addresses in your program. So we're going to talk a little bit today about um, using pointers and pointer operations, passing arguments to functions by reference, using pointers, understanding the const qualifier and how they affect what you can do with a variable. We're going to talk about the size of operator when it comes to variables and types. We're going to use pointer arithmetic to process elements of an array. We're going to look at the relationship among pointers, arrays, and strings. We're going to look at and use arrays of strings some more, and we're going to look at pointers to functions. Additionally, we are going to spend some time talking about some security issues regarding pointers that we need to be aware of when we're using them in our code. So probably the most powerful feature of the C programming language is this idea of a pointer. And of course, with great power comes great responsibility. Pointers allow programs to simulate pass by reference functionality, which allows us to pass a variable by which allows us to pass a variable so that the function can edit it, and that value be stored in the original value. Additionally, we can pass functions between different functions and create and manipulate different types of dynamic data structures, which are data structures that can grow and shrink while we're using them. These are things like linked lists and queues, stacks and trees. These are data structures that we will cover a little bit later in the course. As a matter of fact, when we get around to chapter 10, we're going to look at the use of pointers with structures. And then when we get around to chapter 12, we're going to look at dynamic memory management techniques. So pointers are variables whose value are memory addresses. Normally, variables directly contain an actual value, but when we have pointers, they contain the address to a specific value. In this sense, a variable would directly reference a value, and a pointer would indirectly reference a value. If we are referencing a value through a pointer, we would actually call that indirection. And you can see here kind of a visual example, a way to visualize how this works. We have a variable called count, and it stores the value 7. In the second half of this, we have a variable called count, or count pointer. And it actually points to the value 7 instead. So when we are using pointers, we actually have two things. We have the actual memory location with the value and the pointer variable that contains that memory address, rather than just having a variable that contains that value. Of course, like any type of variable, we do have to define the pointer before we can use it. We do that by using the data type and then a asterisk to indicate that that item is going to be a pointer. So the variable count pointer is a type of integer star, which is a pointer to an integer. So count pointer points to an integer type object, or count pointer points to an integer is a couple different ways you can read that statement. The variable count here would be defined to be an int, not a pointer. Notice that that asterisk is attached to the name of the variable, not the type. That is important to remember. The asterisk when we are defining a pointer is going to come before the name, not come with the data type. Pointers can be defined to point to objects of just about any type. And to prevent ambiguity, when you declare a pointer and a non-pointer variable in the same declaration, you should always declare only one variable per declaration. So just to go back here for a second, I wouldn't do this. What you're seeing here in this example is not something that you'll see me do. The book might do it, but even the book itself, as we just saw on this next slide, says that's generally not a good idea. Pointers should be initialized when they're defined, or they can be initialized when they're defined, or we can assign them a value. A pointer may be initialized to null, 0, or an address, and the null pointer points to nothing. Null is null, and notice that the all caps is what we call a symbolic constant. It is defined in stddef.h. And it may also exist, depending on your implementation, in other headers like stdio.h. Initializing a pointer to 0 is the equivalent of initializing a pointer to null, but null is preferred. When 0 is assigned, it is first converted to a pointer of the appropriate type. The value 0 is the only integer value that can be assigned directly to a pointer variable. Again, however, we prefer to do null. So the address operator, which is the ampersand, returns the address of its operand. So let's assume for a moment I have two definitions. I have an integer y that has the value 5. And then I have a pointer called y pointer, an integer pointer called y pointer. If I have the statement y pointer equals ampersand y, that's going to assign the address, the memory address of the variable y to my pointer y pointer. Y pointer is then said to point to y. And so we're going to see here in just a couple of minutes a schematic representation of memory after that executes. In figure 7.3, the representation of the pointer in memory assumes that the integer y is stored at location 600,000, and that the pointer to variable yptr is stored at a location at 500,000, and the operand of the address operator must be a variable. It cannot be applied to constants or expressions. So we can only get the address of a variable. Now, we've been using that address of operator, and all you guys have used it with so far is when reading in values from standard inputs and using scanf. And again, we've only ever used it with variables. Well, there's a reason why, and that is that we can only use it with variables. If we use it with anything else, it's not going to work. So here we have figure 7.2, and we can see that y pointer is pointing to 5. And what happens is y pointer actually exists at memory location 500,000. And we can see that the value of y pointer at that location is 600,000. And then if we look at memory location 600,000, we see that it holds the value 5. So that is how a pointer works. The pointer holds a memory location, a memory address. It has enough room to store a memory address on the system that it is running on. And it actually then points to, um, it stores that memory address, and then the memory address actually has the value that we're looking for. So we have this indirection operator. It is the asterisk. It is a urinary operator, which is called the indirection operator, or you may hear it referred to as the dereferencing operator. The dereferencing operator is designed to get us the value of the object which the operand or the pointer is pointing to. So if we have a pointer and we want to print out the value that that pointer points to, we need to use the dereference operator to dereference that pointer. If we just use YPTR, we're going to get the memory address printed out. If we use asterisk YPTR, we would get the value 5, because that is the value stored at the memory address that YPTR is pointing to. So we have to use that indirection operator or dereferencing operator to essentially dereference the pointer. I'm not interested in its memory address. What I'm interested in is what's stored there. And again, we'll do that through dereferencing. So we're going to take a look at a program here that demonstrates the pointer operator, the address operator, and the dereference operator. The printf conversion specifier P is designed to print memory addresses as hexadecimal integers on most platforms. If you want to learn more about hexadecimal integers, you can find that in Appendix C. I know we've talked about that before. You'll notice that the address of A and the address of APTR are going to be identical in the output, confirming that the address of A is indeed assigned to the pointer APTR. And the address of operator and the dereference operator complement one another. When they're both applied consecutively to APTR in either order, the same result is printed. So we're going to look at, and then when we're done with this program, we're going to take a look at the precedence and associativity of the operator that we've introduced compared to all of the other operators that we've already talked about so far this semester. So let's start off taking a look at this program. So I've got in my main method, I've got an integer variable with the value of 7. And then I've created a pointer to that integer variable. So I've called it a pointer. And I've assigned to it the address of A. So we are going to print out now the value of the memory address of A. So we're going to use the address of operator to find out where A exists in memory. And we're also going to print out the value of the pointer. We're going to find that these two are the same because, again, the pointer holds a memory address and A exists at a memory address, and we'll see that they point to the same place. When we print out the value of A, or we dereference a pointer or APTR, we're going to see that we also get the same value. And if we do dereference and address of on both of these, we will see that we actually get the same result. So let's take a look at the results of this program. So the address of A gives us 0028FEC0, and the value of a pointer is 0028FEC0. If we just grab the value of A, and if we dereference a pointer, we get 7 for both of those. If we take the address of the dereferenced value of a pointer, we get the memory address. If we get a pointer to the memory address of a pointer, we also get the memory address. So you can see that the values complement each other. We're not going to find many situations where star asterisk or asterisk ampersand and ampersand asterisk are used together. This is just to show you that you can do it, and it doesn't matter which order you do it, you're going to get the same thing, and that is the address of that pointer. The big thing here we're going to want to know is how to assign memory addresses to a pointer, and how to get the values back from those memory addresses of that pointer. So when we talk about order of operations, as we have discussed things so far, obviously parentheses, brackets, prefix and postfix come first. Then our urinary operators, positive, negative, prefix increment and prefix decrement come next. Then not, then address of and the dereference operation. Multiplication, division, and modulus, addition, subtraction, all your relational operators, all your equality operators, and or conditional, your assignments, and then of course any commas. There are two different ways to pass values to pass an argument to a function. We can pass by value or pass by reference. Normally, all arguments are passed by value. However, sometimes functions require the capability to modify variables in the caller, or to pass a pointer to a large data object to avoid the overhead of passing the object by value. If we pass a large object by value, we run into some issues with the time and memory that it takes to make a copy of the object. So we can use pointers and the indirection operator to simulate passing by reference. When a calling function with an argument that should be modified, the addresses of the when we have a function that needs to modify the arguments that the caller has provided, we'll use the addresses of those arguments so that we can make that change. Now, normally we'll accomplish this by applying the address operator to the variable in the caller, whose value is supposed to be modified. Now, we saw in Chapter 6 last week that arrays are not passed using the ampersand operator because C automatically passes the starting location in memory of the array. The name of the array is equivalent to the address of the first item. When the address of a variable is passed into a function, the indication operator may be used in the function to modify the values at the location of the caller in memory. So we can take advantage of that. Now, what we're going to see here in the next two programs that we're going to look at are two versions of a function that cubes an integer. First is cubed by value, then is cubed by reference. 7.6, the program that we're going to see in figure 7.6 passes the variable number by value to the function cubed by value. Cubed by value cubes the argument and then passes it back using a return statement. The new value is assigned to the number, the original number variable in the main method. So let's take a look at that. I will tell you that this is probably the ideal way we want to do something like this. We should avoid reference arguments wherever possible. However, because of the limitations that C has, that isn't always possible. Sometimes we just can't get around it. So we're going to stick with a simple program or with a simple function just to give you an understanding of how this is going to work. Again, ideally we would do things this way because it's a simple function. It's got some data in, one data item out. There's no need to do it by reference. However, because of the limitations of C, we can't always do what we would like to do. So I've got this function called cube by value. You'll notice that it just takes a plain old integer as an argument, and it returns an integer based on its prototype. We have a value 5 we create a variable called number. We set it equal to 5 in the main method. We print out that value. We call our function. We provide it the variable number, and then we assign number the result of that function call. If we look at the function call itself, we will see that the function, again, just like the prototype says, we're going to return an integer value. The function is called cube by value, which we saw from the prototype, and it requires an integer in order to do its work. Inside the body of that function, we are going to return the value of n multiplied by n multiplied by n. So in the case of 5, it would be 5 times 5, which is 25, times 5, which I couldn't tell you off the top of my head what that is without a calculator. And then that'll return back to the main method. Of course, we'll print out the result of that value. So if we look at this, it's 125. I should have realized that. The original value of the number was 5. After we called the function, the result was 125. And again, for something that simple, this is the way I would recommend doing it. However, we need to take a look at, it's often good with these demo programs to use something small and easy to understand to demonstrate the differences. So in the next program, we're going to look at how to pass this by reference. We're going to take a pointer called nPointer in our cube by reference function. The function is going to dereference the pointer and cube the values, and then assign the result back to the pointer, thus changing the number in main. And then we're going to look at how this happens sort of visually once we look at the program. So first of all, notice that the method prototype has changed. This method is no longer returning a value. It doesn't need to. Because we're sending through the memory address, we're actually changing the original value, so there's no need to return a value here. Notice that of course, we've changed the name to better describe what this function does. And then notice that the parameter has changed. Instead of just being an integer, notice that it's an integer pointer. When we are calling cube by reference, notice that because we just have a regular integer number here, we are passing in the address of where the value 5 is located rather than the actual value. Because we are using a pointer, we have to use the memory address. 5 is not a valid memory address. Instead, we need the location where in RAM is 5 stored. So that's going to go into int pointer. Now, we have this pointer, which is a memory address. In order to change the value of that, I need to dereference that pointer. So you'll see that we're dereferencing integer pointer to change the value. And we're setting that equal to the dereferenced value of n pointer multiplied by the dereferenced value of n pointer multiplied by the dereferenced value of n pointer. I know this gets a little bit hard to read because of all of the asterisks. But notice that the dereference value or the dereference operator sticks to the pointer name. What this says is instead of multiplying the memory addresses together, instead multiply together the values at the location of that memory address. And when you're done, store that value at that location of that memory address. We don't want to change the address of n pointer. We want to change the value stored at that address. And again, that's why we need that dereference operation. Again, the result is the same, 5. If we start out with 5, if we cube it, we get 125. So the function receives the address of that argument, all right? Because it's defined as a pointer parameter, it has to be a valid memory address. The header does specify that the cube receives the address of the integer variable as an argument. It stores the address locally in n pointer, and it does not return a value. The function prototype also contains the int asterisk in that parentheses. And again, of course, the names included are ignored by the compiler for the purposes of the prototype. For a function that expects a one-dimensional array as an argument, the function's prototype and header can use the pointer notation shown in the parameter list for cube by reference. The compiler doesn't differentiate between a function that receives a pointer and one that receives a one-dimension array. It's the same thing. This, of course, means the function then needs to know when it's received an array or simply a single variable to perform the pass by reference. When the compiler encounters a function parameter for a one-dimension array in the form of int b brackets, the compiler converts the parameter notation into int star b. And we can do those two forms are completely interchangeable. So let's take a look at cube by value as sort of a visual step-by-step. So first, number is set equal to 5. Then we call cube by value into n, and n is undefined. So in the main method, number is still 5. When we call cube by value, 5 gets passed into it, so n now has the value of 5. After cube by value cubes the parameter n, so we multiply n by n by n, we get 125. We return that value. Back over in main, number is still 5. Cube by value returns to main. That result is stored in number, so that's 125. So now the value of number is going to be 125, and the value of cube by value, n is nothing now. And again, once we complete that assignment, number is 125, n is now undefined because we're not in that method call. If we do this by reference, number is 5. N pointer is undefined in cube by reference. When we call cube by reference, n pointer establishes a pointer to the memory location where 5 is stored. So once we multiply the values at that memory location together, 5 times 5 times 5 times 5, and assign that value to whatever location n pointer is pointing to. Now number has changed to 125, and it has changed everywhere that references that memory address for number. Whether that's through a regular variable or through a pointer, it's changed because we've changed it in memory. Now, the const qualifier enables you to inform the compiler that a value of a particular variable should not be modified. Just because you have a pointer does not mean that you need to change that. So over the years, there was a large base of code that was written in earlier versions of C that did not use const because it wasn't available. And so there were significant opportunities to re-engineer a lot of that old code. 6 possibilities existed for using or not using const with function parameters. 2 with pass by value parameters, and 4 with pass by reference parameters. So how do you choose one of the 6 possibilities? Well, I'm going to introduce you to the concept of the principle of least privilege. Always afford the function enough access to its data, in its parameters to accomplish a specific task, but absolutely no more than what is minimally necessary to do the job. This is the idea of least privilege. So a couple of weeks ago, we talked that all functions in C are passed by value. That means a copy of the argument in the function, a copy of the argument in the function call is made and given to the function. The copy is modified in the function. The original value does not change. In many cases, a value passed to a function is modified by the function so it can do its job. However, there are some instances where we should not be manipulating those values, even though it manipulates a copy of the original function. So let's consider a function that takes a one-dimensional array and a size and prints out the array. That function is going to loop through each element of the array and output each value. The size of the array is used to determine what the upper bound is on the array so that the loop can terminate printing. Neither the size nor the contents really need to be changed. If we attempt to modify those values declared as a constant with const, the compiler catches that and issues either a warning or an error, depending on the compiler that you're working with. There are 4 ways to pass a pointer to a function: a non-constant pointer to non-constant data, a constant pointer to non-constant data, a non-constant pointer to constant data, and a constant pointer to constant data. And each of these 4 combinations provides a different level of privileges, and we're going to discuss each of those here for you. So the highest level of access is non-constant pointer to non-constant data. The data can be modified through dereferencing the pointer, and the pointer can be modified to point to other items. A declaration for a non-constant pointer to non-constant data, we are not going to use the const operator at all. And that would be sort of our very first example there with the cube by reference. That was a good example of this very concept. We could use this pointer to receive string arguments to a function that processes and maybe modifies every character in the string. We might use it when we need to pass a value by reference because we need to change it. Those would be good situations. Let's look at we're going to look at a program that has a function called convert to uppercase. It declares a parameter, a non-constant pointer to non-constant data called S pointer. It's a character pointer. The function processes the array string pointed to by S pointer 1 character at a time. We use the standard library function toUpper from the ctype.h header to convert each character to its corresponding uppercase character. If the original is a non-letter or uppercase is non-letter or is already uppercase, we just get the original character back. Line 23 moves the pointer to the next character in the string. So here is an example. So we have our prototype. It is void. It's called convert to uppercase, and it uses a pointer to a character. We have a string array, a character array called string, characters and $32.98 as the initialized value. We print out that array before, we print out that string before the conversion, and then we print out that string, we convert it to uppercase, and then we print out the string after. Now the real magic is in the convert to uppercase function. So we have this character pointer, we call it S pointer. As long as S pointer does not reference the value, the end of string termination character, that is the /0, or I should say \0, we are going to dereference the current value of that string pointer and call the toUpper function in the ctype.h library with the dereferenced pointer. Remember to dereference your pointers here. We are interested in the values, not in the addresses. And then to move on to the next character, we're simply going to increment the address of the pointer. So we end up with a mixed case on characters before conversion and a mixed case of, or an all uppercase characters after conversion. So it's pretty simple how we do that. So that's non-constant pointer to non-constant data. We have a non-constant pointer to constant data. We can modify the pointer to point to any data item of the appropriate type, but the data to which the pointer points cannot be modified. Such a pointer might be used to receive an array argument to a function that will process each element in the array without modifying it. So let's say we have a point, we're using pointers to pass around an array. We may want to iterate through that array and say display the contents, but we should not be changing that contents. So that would be a situation where we would have a non-constant pointer, because like we saw in the previous example, we'll want to use that pointer to point to every item in the array, but we're not going to be changing the values in that array. So the data itself would be constant, it's not changing, but the pointer needs to be able to change. We're going to look at an example of a function called print characters that declares s pointer to be a type of const char pointer. The declaration is read from right to left as s pointer points to a character constant. The function uses a for statement to output each character in the string until the null character is encountered. After each character is printed, we will increment the pointer to point to the next character in the string. So it's a fairly simple program. So let's take a look at our prototype, because that's the big thing here. So we've got a void again, because we're not returning a value. It's a constant character pointer, so it's a pointer to a character constant. In the main method, we've set up an array of characters called string that prints characters, that says prints characters of a string. So we are going to output the literal, the string is, and then the result of the print characters function, and then a new line. So let's take a look at how we would do this. So we're using the for loop. Notice there's no initialization statement because we're not setting up a loop control variable. The pointer is going to move through the array. Again, notice that we're a const character pointer. If I were to try to alter this program to change the values, change any of the values located in this array, it would not work. I would get an error. I would either get a compiler warning or an error, depending on the compiler that I'm using. But basically, I'm just going to step through each item in this array until I find the null value, and I am going to print that out using a printf statement. Again, I'm dereferencing my pointer for the purposes of examining the value of the pointer at that location, because the pointer points to a memory address, or the pointer contains a memory address. I'm not interested in that address. I'm interested in the value that lives at that address, and so I need that dereference operator. Now this works because I have said the pointer can change what it points to. However, the data that is at that location cannot be changed, and that is all based on that const char asterisk sptr definition in the method header. We're going to look at a program now that attempts to compile a function that receives a non-constant pointer to constant data. This function attempts to modify that pointer, modify the data pointed to by xptr, which results in a compilation error. So here we have an integer y. We've passed the address of y to a function f. Notice up in the prototype that we have const int pointer xref, or x pointer. If I try to change the value of x pointer by dereferencing x pointer and assigning it 100, I will get an error message. In the case of the compiler used for this example, the error is C-2166 L value specifies constant object. So whatever is being pointed to by X PTR is defined as constant and therefore cannot be changed. Okay, so that's how this one works. Printing one character at a time using a non-constant pointer to constant data. Again, this is what we've been doing. As you know, arrays are aggregate data types that store related items under one name. In Chapter 10, we're going to look at another form of aggregate data type called a structure. A structure is capable of storing related data items of different types under one name. For example, we might store information about an employee at a company, so there might be an integer for an employee ID, a string for a last name, a string for a first name, parts of an address, a string for a zip code, a string for a number of years they've worked with the organization, a decimal value, a double for or a float for payroll, for hourly rate, or something like that. When a function is passed with an array as an argument, the array is automatically passed by reference. However, structures are always going to be passed by value. That means a copy of that entire structure will be passed. That's going to require some execution time overhead to make a copy of each data item in the structure, storing it on the function's call stack. When the structure data must be passed to a function, we can use a pointer to constant data to get the performance of pass by reference and the protection of pass by value. When a pointer to a structure is passed, only a copy of the address at which the structure is stored must be made. On a machine with a 4-byte address, a copy of 4 bytes of memory is made rather than a copy of a much larger structure that may take way longer than 4 bytes. Basically, if memory is low and execution efficiency is a concern, we need to use pointers. If memory is in abundance and efficiency is not a major concern, pass by value enforces least privilege. So when we're dealing with small stuff and you're talking about a desktop computer, pass by value is fine. You have more than enough horsepower for the necessary overhead. You have more than enough memory for the necessary overhead. However, if you are on a memory-constrained system, like an embedded device, or you are looking for execution efficiency is paramount, that's where pointers are involved. Some systems enforce const well, so pass by value do not enforce const very well, so pass by value is still the best way to prevent data from being modified. A constant pointer to non-constant data always points to the same memory location, but the data can be modified. This is the default for an array name. The array name is a constant pointer to the beginning of the array. All data in the array can be accessed by and changed by using the array's name and the index. The constant pointer to non-constant data can be used to receive an array as an argument to a function, and that array accesses the array elements using only index notation. Pointers that are declared constant must be initialized when they're defined. If the pointer is a function parameter, it's initialized when the pointer is passed to the function. We are going to look at an attempt to modify a constant pointer. When a pointer PTR is defined to be of type int star const. So for a constant pointer, the const keyword goes between the star and the pointer name. The function is read as left to right, as PTR is a constant pointer to an integer. From right to left, as PTR is a constant pointer to an integer. The pointer is initialized with the address of the integer variable x. The program attempts to assign a value of the address of y to pointer, and of course it generates an error message. So we have int x, we have int y. When I am creating a pointer, if I put const between the star and the name of the pointer, that makes the pointer itself constant, as we see here on line 12. That means the address of PTR cannot change. It will always point to the address of x. If we try to change that, it's not going to work. So I can assign the value 7 to that pointer, but I cannot assign that pointer a new address. Again, we get that same error that the left value specifies a constant object. Least privilege access, the least access privilege is granted by by setting the pointer to be constant and point it at constant data. In this case, the pointer can't change and the value of that memory location cannot be changed. This is how the array should be passed to a function that only looks at the array using index notation and does not change the array. And we are going to take a look at a program here that does that. Figure 7.14 is going to point a variable PTR to be a type of const. Int const, which is read from left to right, is pointer. PTR is a constant pointer to an integer constant. And we are going to attempt to modify the data that pointer points to and attempt to modify the address that that PTR points to. And in both cases, we are going to get errors. So let's take a look at this. So I have a constant pointer to constant data. The value or the address location is going to be X, which has the value 5 stored in it. It's going to be the address of the integer variable X, which currently has 5 in it. I'm going to print out that value. Then I'm going to change the value that pointer points to. I'm going to change it to 7. I'm going to dereference pointer and I'm going to assign it 7. But that's going to break because when we created this pointer, we said it's pointing to constant data. That means that that pointer cannot change the value of X. Now I'm going to try to change the pointer to point to the variable Y. Well, I can't do that either because I said that it is a constant pointer to constant data. A constant pointer means that I cannot change the memory address. So this is least privilege. If you are assigning an array that you are going to use array notation to access, and you only want to be able to view the items in the array, this is how you would do it. This would ensure that your function cannot change the values of the array and cannot be pointed anywhere else. Now, let's take a look at the bubble sort. We are going to alter that bubble sort to use two functions. We're going to use a bubble sort. We're going to use we're going to have a function called bubble sort, and it's going to also take advantage of a function called swap. The function bubble sort sorts the array. The function swap is called to exchange the items of array I and array I plus 1. Remember that C is going to enforce information hiding between functions. So swap is not going to have access to individual array elements in bubble sort because bubble sort wants swap to have access to the array elements to be swapped. Bubble sort has to pass each of these elements by reference to swap so that the addresses of the array are passed explicitly. Although entire arrays are passed automatically by reference, individual array elements are scalar values and so are ordinarily passed by value. Therefore, bubble sort uses the address operator on each array element in swap to call or in the swap call to effectively pass by reference as follows. So if I want to pass the memory addresses of array.j and array.j plus 1 so that we can properly swap those items, I have to do that with pointers. This is a situation where you would have to use pass by reference because we cannot return two values from a function call. This is a really good example of where a really appropriate use of pass by reference is invoked here. Even though swap, because of information hiding, is not allowed to know the name of the array, swap may use the pointer element PTR1 or the pointer element 1 PTR as a synonym for array.j when the swap references the references pointer element element 1 PTR, it's actually referencing array.j. Similarly, when swap references the pointer element 2 PTR, it is actually referencing array j plus 1 in bubble sort. So we're actually sending the addresses of those two individual array locations in memory so that we can mess with them, really. I think that's probably the best way to put that. Even though swap is not allowed to say array j equals hold, and array j then equals array j plus 1, array j plus 1 equals hold, we can achieve the same effect by simply saying hold equals the dereferenced element 1 PTR. Dereference element 1 PTR holds the value by dereferencing element 2 PTR, and then we can change the value at element 2 PTR by dereferencing element 2 PTR equals the value hold. And again, I'm using that dereference operator. So let's take a minute now and look at some code that I just sort of introduced to you. Let's look at this code here on this for this bubble sort. So we have our main, first of all, we have our bubble sort function parameter. We're taking a constant pointer to an integer, that's going to be our array, and a constant value of size t, so that we're not changing those values. We create our array of size. Size is a precompiler definition. It's going to be 10 items. We have the array 2, 6, 4, 8, 10, 12, 89, 68, 45, 37. Those are our array items. We are going to print them out in original order. We are then going to call bubble sort. We are going to, let everybody know we're printing out those items in ascending order, and then we're going to print out the array, and then finally just a blank line. If we look at bubble sort, you can see that inside bubble sort we have a prototype for a swap method. We will look at that swap method in just a second. Notice that swap method takes two integer pointers, one for element 1, one for element 2. If we need to do a swap, we are going to call our swap function, and we are going to pass it the addresses of the two values that we wish to swap. When we get into our swap function, you will see that we have two pointers. We're going to dereference element 1 PTR and store its value in hold. We are going to dereference element 2 PTR and store it in the location referenced by element 1 PTR. Again, we have to dereference both pointers to make that happen. We're then going to dereference the element 2 PTR, and we're going to, in that location, we are going to store the value of hold. So essentially we have done our swap, but this time we have done it with pointers rather than actual array elements. And this is actually a good idea because, again, our function should only be doing one thing. The whole point of the bubble sort function is to determine if we need to make a swap. We have another function then whose sole job is to do the swap, and this is really good readable code. If you go back to the bubble sort function, you can see that this is very readable as far as the bubble sort goes, right? If I were to give this to you, a code to you, and say, hey, this is how the bubble sort works, you could probably figure this out. Why? Well, okay, I'm going to go through each item in the array, and then I'm going to have, 9 passes through the array, and then I'm going to look at each item on each pass, and if the first item is bigger than the item next to it, we're going to swap those items, right? That's essentially what the bubble sort does in a nutshell. And I think this is far cleaner and clearer to read than the original bubble sort function that we looked at last week. And that is because we are using that swap method, whose job is to simply swap values when appropriate. So I think that makes things very, very easy. So several features of the bubble sort function should be noted. Of course, our function header declares an array as an int pointer const rather than an integer array to indicate that the bubble sort receives a one-dimensional array as an argument. Again, doesn't matter. These notations are interchangeable. Parameter is the parameter size is declared as a constant to enforce that idea of least privilege. We don't need to be making any changes to size, and nobody should be making changes to size in our function. Although the parameter size receives a copy of the value in main, modifying the copy cannot change the value in main. Bubble sort does not need, and that's the key, does not need to alter size to accomplish its task. So therefore, we should not let it. The size of the array is going to remain fixed during the execution, so therefore, there's no reason to change it. The prototype for function swap is included in the body of the function bubble sort, because bubble sort is the only function that will call swap. So we can prototype a function inside the body of another function if that function is going to be the only thing that calls it. Otherwise, I would say put your prototypes at the top of your program. And I'm just kind of a stickler. Just put them all up there anyway, because you never know when somebody else might want to use a function. It really doesn't make any sense to me to create a function and then limit it to only certain function calls. I think it should be available anytime you need to make a swap. So I would have put it up at the top, but that's okay. Placing the prototype bubble sort in bubble sort restricts proper calls of swap to those made from bubble sort. Other functions that attempt to call swap do not have access to the proper function prototype, so the compiler is going to generate one manually. Normally this results in a prototype that does not match the function header and will generate a compiler warning or an error because it assumes int for the return type and the parameter types. But, again, I don't know that that's a good thing. I guess that's kind of a design thing. If that's how you want to do your design, I guess that's okay, but I'm not a big fan of that. The function bubble sort receives the size of the array as a parameter. The function must know the size in order to sort the array. Okay, we have to know the size. We can't just go through until we hit some sort of null termination character. Of course, this isn't a string, so that's not even an option here. This is an integer array. We have to know that size in order to sort this array. When the array is first passed to the function, the memory address of the first element is received by the function. The address, of course, does not convey the number of elements. Therefore, we must always pass around the size. Another common practice to pass a pointer to the beginning of an array and a pointer to the location just beyond the end of the array. We'll talk about that a little bit later today. The difference between the two pointers is the length of the array, and the resulting code is a little bit simpler. C++ and Java have made this a little bit better with that length property that they have available to an array, but we don't have that in C. This was one of the things that both of those languages had determined would make C better, so they implemented it as part of that. But we can kind of do that ourselves with this technique that was just talked about and that we're going to see just a little bit later in our discussions. In the program, the size of the array is explicitly passed to bubble sort. There are two main benefits to this approach, of course, is reusability and proper engineering functions. By defining the function to receive the array as an argument, we enable the function to be used by any program that sorts a one-dimensional array of any size. So this is called dependency inversion. By explicitly identifying what this function needs to do its job, we know that, and that also makes the function more usable because because we know what those dependencies are, we can use it anywhere where we have those two dependencies. Um, so not only does this promote the idea of reuse or code reuse, it also promotes the idea of dependency inversion where are all of the necessary dependencies are taken in as parameters, and so that helps us for reuse. It helps for testing. If we had a testing suite, we could actually test the individual function calls. If we might be able to test the individual function calls depending on the application, or we could write a test harness with this code in it. So this is a really good thing. We could have stored the array size in a global variable that's accessible to the entire program. This would have been more efficient because then a copy of size would not be made to pass a function. However, other programs might require an integer array sorting capability, so and they may not have a global variable, so that function couldn't be used in those programs. And again, that violates this concept of dependency inversion. Spelling out all of your dependencies up front so we know what is required to use a particular thing. And so that's just a good software engineering practice that has been around since the 80s, I think. The size of the array could be programmed directly into the function. Again, this restricts reuse to functions of a specific size, and again, does not spell out dependencies very well. Right? A sorting array is dependent upon a sorting function is dependent upon an array and the size of the array. The size of operator is a special operator that C provides to determine the number of bytes in an array or any other data type. If we apply the size of operator to the array that we're going to see in the next program in figure 716, it's going to return the total number of bytes in the array as a type T, which is an unsigned integer. The variable type of float on the computer that this program was run on uses 4 bytes of memory, and the array is defined to have 20 elements. Therefore, the array takes up a total of 80 bytes. If we know how big the data type is on a particular computer or implementation, and we know the number of bytes that the array takes up, we can calculate its length with a degree of certainty. So we are going to create a method called getSize, and it is going to take a float pointer. It is going to return a size T object or a size T value. We are going to set up an array to hold a float array to hold 20 items. The number of bytes in the array are going to be size of array. We're going to use size of array, and we are going to return the number of bytes by getSize. And so in both cases here, we are looking at the array as well as the pointer and calling essentially size of. And if we look at getSize with the pointer, we are going to get the size 4 because that is going to tell us the number of bytes in the individual float item, and then the number of bytes in size of the array is going to tell us how big the array is. So what does this mean to us? Well, the number of elements in the array can also be determined with size of. For example, if I have a double I have an array called real of doubles that have 22 doubles. Doubles are normally stored as 8 bytes of memory. So the array real contains 176 bytes. If we take the size of real divided by the size of real index 1, we can determine the number of elements. Basically, what we're doing here is by taking the size of the first item in real, we are getting the size of the data type. We are determining the size of the data type at runtime. So then we don't have to worry about knowing what those definitions are in the headers. Even though getSize is receiving an array of 20 elements as an argument, the function's parameter PTR is simply a pointer to the first element. When you use size of with a pointer, it returns the size of the pointer, not the size of the item to which it points. Since the size of a pointer on our system is 4 bytes, getSize returns 4 bytes. Also, the calculation in the program for determining the number of array elements using size of works only when using the actual array, not when using pointers to the array. So that's something else that you have to keep in mind. We're going to look at a different program now that's going to allow us to determine the sizes of basically the standard data types, as well as an array and a pointer, so that we can see the differences. Now, of course, the results of this program are going to be implemented differently across different platforms, and sometimes across different compilers on the same platform. So if you decide to write this program and see what the results are on your computer, you may get different values. I just want to point that out to you right now. So the first thing that we've done in our main method is we've declared a variable of every type. So we have a character, a short, an int, a long, a float, a double, a long double, an array of 20 characters, and a pointer to that array. And essentially, we are going to call printf. We're going to get the size of character, the size of short, the size of int, the size of long, the size of long, the size of float. We're going to get the size of double, the size of long double, the size of the array, and the pointer to the array. And you can see all the different size ofs that I am passing into all the different size ofs that I'm passing into the printf function. So a character is a single byte. A short is 2 bytes. An int is 4 bytes. A long is 4 bytes. A long is 8 bytes. A float is 4 bytes. A double is 8 bytes. A long double is 8 bytes. The array is 80 bytes, and the size of a pointer is 4 bytes. So those are just for some comparisons for you. We can apply it to any variable name, type, or value. When applied to a variable name that's not an array name or a constant, it's the number of bytes used to store that specific type of variable or constant. Parentheses are required when using a type. When a type is supplied as one of size of's operands. Pointers are valid operands in arithmetic expressions. Okay, I apologize, we're switching gears here. So pointers are valid operands in arithmetic expressions, assignment expressions, and comparison expressions. However, not all the operators normally used with these are valid in conjunctions with pointers. So we're going to talk now about operators that can have pointers as operands and how those operations are used. A limited set of mathematical operations can be performed on pointers. We can increment, decrement, we can add, We can do the shortcut assignment with pointers. We can subtract a pointer from a pointer, and a pointer may be subtracted from another pointer, and this is only meaningful when the pointer points to the same item in an array. So we can add an integer to a pointer, subtract an integer to a pointer, and subtract 2 pointers from the same array. Let's assume we have an array of integers called v. It's got 5 items. The first item is located at location 3000 in memory. Then we have v pointer, which has been initialized to point to v index 0. So v pointer is also pointing to 3000. The next image that we're going to look at illustrates the situation for a machine with a 4-byte integer. The vptr can be initialized to point to the array v with either of the statements. So right now we've got a pointer that's pointing to location 3000. And if every integer is 4 bytes in length, that means the next integer starts at 3004, and then the one after that at 3008, and then 3012, and then 3016. In conventional arithmetic, 3000 plus 2 yields the value 3002. However, this isn't how pointer arithmetic works. When an integer is added or subtracted from a pointer, the pointer is not incremented or decremented simply by that integer, but by that integer times the size of the object to which it points to. So the number of bytes depends on the size of the object. For example, if we were to do vptr plus equal 2, that would actually produce 3008, because 3000 plus 2 times 4, because remember, integers are 4 bytes on this system. So we actually move 2 integers. Adding 2 to 3000 means to move 2 integers, not move 2 bytes. So that's important to remember. In that case, in array v, vptr would now point to index 2, which we will see in the next image. If an integer is stored in 2 bytes of memory, then the memory location would be 3004. Again, we're still moving. When we move 2 in a pointer, we're not just adding 2. We're adding 2 complete integers, or 2 complete doubles, or 2 complete longs, or 2 complete shorts, or 2 complete characters when we add 2 to a pointer. If the array were a different type, it would increment that pointer by twice the number of bytes it takes to store an object of that type. Again, we're moving essentially 2 elements. We're adding 2 elements on, or 2 indexes on to where we're pointing. If we perform pointer arithmetic on a character array, the result will be consistent with regular mathematics, because a character is 1 byte long, right? So that's going to work. But again, if we're thinking about integers, and integers are 4 bytes, if I add 2 to vptr and I start at 3000, I'm actually going to move the size of 2 integers. So if the first integer is 4 bytes, it starts at 3000, it ends at 3004. I'm going to move 3004 is 1 integer. 3008 is 2 integers. So I'm going to move 2 spots, 2 integer spots in memory. So think about it as, if you're adding or subtracting values from pointers, you're not adding or subtracting individual bytes. You're adding or subtracting individual objects. So if it's an integer, you're adding or subtracting individual integers from that pointer, especially when we're talking about an array. That means you're moving 1 whole spot in that array. if we had, if VPTR had been incremented to 3016, which points to index 4, the statement VPTR minus equals 4 would actually set VPTR back to the beginning of the array. If a pointer is incremented or decremented by 1, we can use the increment and decrement operator. So either plus plus VPTR or VPTR plus plus will move the pointer to the next location because we're adding 1. Well, remember, we're not just adding 1 byte, we're adding 1 memory location, 1 size of an integer to that pointer's address. Again, either statement minus minus VPTR or VPTR minus minus will move us backwards 1 whole element in the array. And pointer variables can be subtracted from one another. So let's, for example, I have a pointer that points to the location 3000, and I have a second V2 pointer that contains the address 3008. I could do VPTR2 minus VPTR1, and that would assign to X the number of array elements between VPTR2 and VPTR1. In this case, it's 2 array elements, not 8, even though there are 8 bytes between the two. Remember, with pointer arithmetic, we are doing not necessarily the number of bytes, but the number of objects taken up by those bytes. Pointer arithmetic is undefined unless we are performing it on an array. We cannot assume that 2 variables are of the same type are stored contiguously in memory. That means that we can't assume that they're next to each other in memory unless they are stored in an array. We can assign, a pointer can be assigned to another pointer if they both have the same type. The exception to this rule is a pointer to void, which is a generic pointer that represents any pointer. All pointers can be assigned to a pointer of void, and a pointer of void can be assigned to all pointers. In both cases, a cast operation is not required. A pointer to void cannot be dereferenced. You cannot point to nothing. Consider this. The compiler knows that a pointer to int refers to 4 bytes of memory on a machine with 4-byte integers, but a pointer to void simply contains a memory location for an unknown data type. The precise number of bytes to which that pointer references is not known by the compiler. The compiler has to know the data type to determine the number of bytes to be dereferenced for a particular pointer. Pointers can be compared using equality and relational operators, but such point comparisons are meaningless unless the pointer points to an elements of the same array. Pointer comparisons to compare addresses pointer comparisons compare the addresses stored in the pointers, not the actual values. The comparison of 2 pointers pointing to elements in the same array could show, for example, that one points to a higher numbered element than the other does. The common use of pointer comparisons is determining whether the pointer points to null or nothing. Pointer arrays and pointers are intimately related in C and are often used interchangeably. An array name can be thought of as a constant pointer. Pointers can be used to do any operation involving array indexing. And let's assume that we have an integer array B with 5 items. The integer pointer BPTR and a BPTR have been defined. Because the array name without an index is a pointer to the first element of the array, we can set BPTR equal to the address of the first element in array B with the statement BPTR equals B. We don't need an address of operator. We could use it. It's not going to make a difference. But we can use... or no, I'm sorry, we can't because that would make a difference. We can just use B, because B contains the address. It is equivalent to saying the address of the first element of the array. It is the same as doing that because B contains the address. Array element 3 can be referenced as by dereferencing the pointer plus 3. The 3 in this expression is considered an offset, remember, because we're moving 3 integers, not 3 bytes. When the pointer points to the array, the first element of the array, the offset indicates which array element should be referenced, and the offset value is identical to the array index. This is called pointer offset notation, for those of you people who are interested in vocabulary. The parentheses are necessary because the precedence of the dereference is higher than the precedence of the plus. So because of that, we have to use the parentheses to force it to do what we want it to do. Without the parentheses, we would be grabbing the value of the value stored at bptr pointer, and 3 would be added to whatever the value of the first index of the array is. Just as an array element can be referenced, just as the array element's address can be referenced with the address operator B3 or B index 3, we can write that same thing as a pointer expression bptr plus 3. The array itself can be treated as a pointer and used in pointer arithmetic if we want. So, for example, the expression pointer to b plus 3 can also refers to b index 3. In general, all indexed array expressions can be written in pointer offset notation. In this case, pointer offset notation was used with the name of the array as the pointer. The precedence is the precedence statements, or the preceding statement does not modify the array element in any way. B still points to the first element of the array. Pointers can be indexed like arrays too if we want. So we could say if a bptr, it points to the first index of the array, or points to the value of index 0, or points to the address of index 0 of the array, I can do b square brackets 1 if I wanted to. That's called pointer index notation. Remember that an array name is essentially a constant pointer, always pointing to the beginning of the array. So b plus equal 3 is invalid because it attempts to modify the value of the array name with pointer arithmetic. We can't do that because it's a constant pointer, and so that means we can't change that value. We are going to look at another program here. We're going to use 4 methods we've discussed for referring to array elements: array index, pointer offset, array name as a pointer, and then pointer indexing, and pointer offset notation with a pointer to print the 4 elements of the integer array B. So let's take a look at that program. So I've got an array of 4 items, 10, 20, 30, 40. I've also created a pointer to an integer pointer to point to that array. The very first thing I'm going to do is just loop through the array and print out all the items the way we are used to, right? I equals 1, I less than the size, I plus plus. We're just going to do standard array index notation. B index I, which, B index 0 is going to print out 10. B index 20 is going to print out, or B index 2 is going to, B index 0 is going to print out 10. B index 1 is going to print out 20. B index 2 is going to print out 30. B index 3 is going to print 40. We're going to look at pointer offset notation. Pointer offset notation is kind of nice because we are going to increment the offset instead. So we're going to start at offset of 0, right? That's the first index of the array is 0. We are going to, while the offset is less than the size of the array, so while the offset's less than 4, we're going to increase that offset by 1. When we print out the item, instead of doing array index notation, we are going to take B. We are going to add the offset to it. That's going to move us 1 integer or 1 element of the array. And then because B is a pointer, or B is a constant pointer, we are going to dereference the whole thing. Again, remember that B, when we define an array, the array variable name becomes a constant pointer to the first item in the array. Now we are not changing what B points to. Instead, we are simply adding a value to B. We are not changing it. Notice there's no assignment, right? We're just adding an offset essentially. We can loop through B with pointer index notation. We can do BPTR and use indexes just as if it were an array. And it will do the same thing as pointer offset notation, which we see down below, which is very similar to what we did with array offset notation above. The only difference is we're using our pointer this time. Again, we're not changing what BPTR points to. There's no assignment operation here. It is just simply taking it, adding a value to it, and dereferencing that memory location. And we can see in the results on the next slide that it is basically the same. Just to give you an idea of how that works. So let's talk about string copying with array and pointers. If we want to think about the interchangeability of array and pointers, string copying is a great example of how to do this. So we have copy1 and copy2 within the program. Both functions copy the string into a character array after a comparison of the function prototypes. For copy1 and copy2, the functions are going to appear identical. They do accomplish the same task, but they're implemented differently. And that's one of the great things about functions. We don't need to know how they do their work to utilize them. We just simply need to know what we're going to get back and what data we need to give them. And so when we look at this program and we look at those two prototypes, they look almost the same. We've got two constant character constant pointers. And then in the second one, we've got a character pointer and a constant character pointer, or a pointer to constant character data. So we're going to make a string that says hello, and we're going to copy it from string 1 to string 2. And then we're going to create a string 3 that says goodbye, and we're going to copy that from string 3 to string 4. So let's take a look at how that works. So for copy 1, we're going to loop through the string. And we're not going to do anything inside the body. Basically what we're going through is we are assigning the index from string 2 to string 1. Or yeah. And we're doing that, and as long as that succeeds and it is not the null character, we're going to continue. So that's what we're doing here, where we are string 2 has hello, string 1 does not, and we want to put hello in string 1. And so we're looking at every item in the array, and we are taking the value at that particular index, and we are putting it in the other one. And that's why we have a constant string to constant data in S2, and a pointer to a constant pointer to non-constant data in string 1. Because string 1 is what we are changing, and you can see that by the assignment operation in the comparison, because remember the result of an assignment is the value that was assigned. So we're going to continue this assignment until we come across that null termination character, and then we're going to stop. To use copy 2 is going to be a little bit different. String 1, and we have a constant, we have a non-constant string, or a constant, non-constant pointer to non-constant data with S1. With pointer S2, we have a non-constant pointer to constant data. And in this case, we are simply dereferencing the values, and we are incrementing each one of the pointers. So we are moving those pointers through until we go. So we're using pointer notation and we're using array notation in each of these copies, and those are pretty cool copies. In both cases, we're not doing anything inside the body of the for loop. We're doing it all right in the sort of the definition part of that for loop, which is pretty cool. So copy 1 uses array index notation to copy the string s2 into the character array s1. The function defines a variable I as the array index. The for statement header performs the entire copy operation. The body is empty. The header specifies that I is initialized to 0 and is incremented one by one on each iteration of the loop. And so we assign the value of s2 to the current character at s2, whatever the index is, to s1 at that same index. When the null character is encountered in s2, it is assigned to s1, and the value of the assignment becomes the value assigned. And the value of the assignment becomes the value assigned to the left operand, which is then tested, and so that loop terminates. Copy 2 uses pointers and pointer arithmetic to copy the string from S2 to the character array at S1. Again, the for statement in the header performs the entire operation. The header does not include any variable initialization because both of those start at the beginning of their respective string arrays. The copy expression is the dereferenced location of current S1 pointer to the dereferenced location of the S2 pointer. The S2 pointer is dereferenced, resulting in a character that is assigned to the dereferenced pointer in S1. After the assignment in the condition, the pointers are incremented to the next element by adding 1 to them. So S1 moves to the next character in the array. S2 moves to the next character of the string. When the null character is encountered, it is assigned to S1. And then that becomes the result of the assignment, which is compared against that test, that Boolean test, which then becomes false, and so the loop terminates. The first argument to both copy 1 and copy 2 must be an array large enough to hold the second string, or the second argument. Otherwise, we're going to get an error if we run off the edge of the array. Also, the second parameter of each function is declared as a constant, a pointer to a constant string. Again, that's because we are not modifying. That second argument is copied to the first. The characters are read one at a time, but the characters are never modified. So the second parameter is declared to point to a constant value, because the principle of least privilege requires that So if we want to enforce least privilege, we have to do that. Neither function requires the capability of modifying the second argument, so neither function is provided with that capability. We don't want to do that unless we need to do it. So that's something that you want to think about. Arrays can contain pointers. Common use of an array of pointers is to form an array of strings, or a string array. Each entry in the array is a string, but in C, a string is essentially a pointer to the first character of the string. So an entry into an array of strings is actually a pointer to the first character of a string. So consider the definition of the string of the array suit, which represents the different suits in a deck of cards. So I might have a const character pointer of 4 items, and it may contain hearts, diamonds, clubs, and spades. The suit 4 portion of the element indicates an array of 4 elements. The character pointer portion indicates that each element of array suit is a pointer to a character. The qualifier const indicates that the strings pointed to by each element will not be modified. So the 4 values placed in the array are hearts, diamonds, clubs, and spades. Each is stored in memory as a null terminated character string that's 1 character longer than the number of characters between the quotes, as a string is stored. So the 4 strings are 7, 9, 6, and 7 characters long. Although it appears that these strings are being placed in the suit array, only pointers are being stored in the array. Each pointer points to the first character of the string. Even though suit array is fixed in size, it provides access to character strings of any length, and this is probably one of C's most powerful an example of one of C's very powerful data structure capabilities. So suit index 0 is actually a pointer to the array or string HEARTS termination character. Suit index 1 actually is a pointer to the array or pointer to the first character of the array diamonds, the array of characters that represents diamonds with an end termination character. Suit index 2 to clubs, and suit index 3 to spades. And this, again, is kind of a graphical representation of that in memory. The suits could have been placed in a 2-dimensional array with where each row would represent a suit and each column would represent a letter from the suit name. Such data structure would have a fixed number of columns per row, and that each number would have had to be as large as the largest string. That could waste memory. Therefore, when storing a large number of strings, especially if those strings were shorter than the longest possible string. So that is something that we need to be aware of. Now we're going to take a look at a card shuffling and dealing simulation. We are going to use random number generation to develop a card shuffling and dealing simulation program. The program can be used to be implemented to play different card games. To reveal some subtle performance problems, we've intentionally used some suboptimal shifting and dealing algorithms. In this chapter's exercise and in chapter 10, we will develop slightly more efficient algorithms. We're going to use top-down stepwise refinement to develop a program that will shuffle a deck of 52 playing cards and then deal each of the 52 playing cards. So the top-down approach is particularly useful for attacking complex problems. We've seen that in earlier examples. We're going to use a 4x13 2-dimensional array deck to represent a deck of playing cards. Each row corresponds to a suit. Row 0 corresponds to heart, 1 to diamonds, 2 to clubs, 3 to spades. The columns are going to be the face value of the cards, 0 through 9, ace through 10, and then 10 through 12 are jack, king, and queen, or jack, queen, and king. We're going to load the string array suit with the character strings that represent the 4 suits, and the character string face with the character that represents the 13 face cards. So here's what the array would look like. We're going to have we would have a table, and the row 0 is going to be hearts, and the column 0 would be aces, column 1 would be 2, column 2 would be 3, on, with king being 12. If I had a reference to index 2, index 12, that's going to be row 2, that's going to be clubs, and then column 12, which would be kings. So that would be the king of clubs. The simulated deck may be shuffled as follows. First, the array deck is cleared to zeros, then a row 0 to 3 and a column 0 to 12 are chosen at random. The number 1 is inserted at the array element row column to indicate that the card will be the first one dealt. That process will continue up to 52, being up to the number 52. Being randomly inserted into the deck array to indicate which cards are placed first, second, third, fourth, fifth, sixth, all the way on up to 52nd in the shuffled deck. As the deck array begins to fill with card numbers, it is possible that a card will be selected again, and that card will be non-zero when it is selected. In that case, we're simply going to ignore it and until we find an unselected item. Eventually, the numbers 1 through 52 will occupy the 52 slots of the array. At this point, the deck of cards would be considered fully shuffled. Now, the shuffling algorithm can execute indefinitely if cards that have already been shuffled are repeatedly selected in random order. This phenomenon is what we call indefinite postponement. Now, you guys actually experienced some indefinite postponement in the computer-aided instruction assignment. Many of you had your random number generators not generating random numbers correctly. Either they were not generating numbers within the right value, or you weren't seeding your random number generator properly, and so you weren't pulling back the expected mathematical problems, and so the answers that were provided were never matching what your program expected. So what was happening was you were constantly finding yourself asking for an answer, never receiving that correct answer, and your program never ending. So this is the same thing. This phenomenon that you were experiencing in that program is called indefinite postponement. And we are going to discuss a better shuffling algorithm that eliminates the possibility of indefinite postponement. And so just something to keep in mind in the future. When dealing the first card, we just search the array for where row and column equal 1. And this is accomplished with nested for statements, right? We just look at every row from 0 to 3, and then we look at every column and every row from 0 to 12. When a card, what card does that element correspond to? Well, the array suit has been preloaded with the 4 suits, and so we can just do suit.row, and that our suit index row. And then similarly, to get the face value of each column, we can print the character string face column. And then we can also print the character string of. And this is a program that we're going to look at. Printing this information in the proper order enables us to print cards in the form of king of clubs, ace of diamonds, so on and so forth. So let's look at this top-down stepwise refinement. So the basics are here. I want to shuffle and deal 52 cards, right? That's what I want to do. So what's our first pass through in figuring out what that needs to look like? Well, first I have to initialize the suit array, then I have to initialize the face array, then I have to initialize the deck array. Then I need to shuffle the cards, then I need to deal the cards. All right. So I could probably start writing functions for all of these items and have a pretty good start. Those functions might not have implementations at this point, but I could write this as functions in a main method, and that would give me a good start. So what does shuffle the deck mean, though, right? So I have this concept of shuffling the deck, and that might make a great method, but then what is that method going to do? Well, shuffling needs to be expanded. Basically, for each of the 52 cards, I'm going to place a card number in a randomly selected unoccupied slot of the deck. Now, what is deal 52 cards going to do? Well, for each of the 52 cards, I'm going to find the card number in the array and print the face and suit of the card. Now, if I want to incorporate those expanded statements from the second refinement, initialize the suit, initialize the face, initialize the deck arrays. For each of the 52 cards, place a card number in a randomly selected unoccupied spot of the deck. And then again, for each of the 52 cards, find the card number in the deck array and print the face and suit of the card. Okay, that's pretty straightforward. Place a card number in a randomly selected unoccupied spot of the deck. We can probably expand that out a little bit more to while the chosen slot of the deck has been previously chosen, choose a slot in the deck randomly. While the slot of the deck has been previously chosen, choose another deck randomly. Place the card in the chosen slot. Find a card in the deck might be for each slot of the deck array if the slot contains a card number. If the slot contains the card number that we're looking for, print the face and suit of the card. If we expand our third refinement out, we get a little bit more detail if we add those items in. And now we probably have something that we can start to work with. So this is essentially the entire refinement process. The program is more efficient if the shuffle and dealt portions of the algorithm are combined so that each card is dealt as it's placed in the deck. We've chosen to program these operations separately because normally the cards are dealt after they're shuffled, not while being shuffled. The card shuffling and dealing program is showed in the next image that we're going to look at, which is 724 in your book. And the sample execution is shown in 725. We're using the format conversion specifier %s to print the strings. The corresponding argument to the printf call must be the pointer to a character array or a character array. The format specification %5s of %-8s prints the character string right justified in a field of 5 characters followed by of, and a character string left justified field of 8 characters. The minus sign means left justification. No sign means right justification. That means leading versus trailing spaces. So we've got three pre-compiler definitions. There are 4 suits. There are 13 faces. There are 52 cards. I've got a prototype for shuffling. I've got a prototype for dealing. The shuffle prototype takes one unsigned integer array of deck with one unsigned 2-dimension array integer array of deck. The deal has a 2-dimensional integer array of deck, a character interface, the constant character pointer to the array of characters called face, and a constant pointer to the character array suit. We are going to initialize the deck to be all full of zeros. We are going to seed the random number generator, and then we are going to shuffle the deck. We are going to initialize the array of suits. We are going to initialize the array of faces. And then we are going to deal the deck. So let's go take a look at those functions. So again, shuffle just takes the 2-dimension array of deck. And shuffle's pretty simple, right? For each item in the, for each of the cards, choose a slot at random. So we've got 52 cards to look at. We are going to randomly generate a row number and a column number, and then we are, as long as that row and column are not 0, we are going to place our value or place that card number in that location. Once we have placed all the card numbers, we're going to call the deal function. So we are going to deal each of the cards. So we're going to go for every card. We are going to loop through the rows, which are the suits. We are going to loop through the columns, which are faces. And we are going to find each card number. So we're going to start at card number 1. We're going to go to card number 52. And we are going to find number 1, and then we're going to find number 2, and we're going to find number 3, and we're going to print those out. We're going to print those out in a 2-column format so that in this particular run, the very first card that after we shuffled the deck, the card on top was the 9 of hearts. Then the Queen of Spades, the Queen of Hearts, the King of Hearts, the Jack of Diamonds, the Seven of... Oh, no, wait. It would be the Nine of Hearts, the Five of Clubs, the Queen of Spades, the Three of Spades, the Queen of Hearts, the Ace of Clubs, on and on and on, and you'll have all 52 cards. So that's pretty simple. That's pretty good. There's a weakness. Once a match is found, the two inner four statements continue searching the remaining elements of the deck. We will correct that in this chapter's exercise and in the Chapter 10 case study. There is a way out of that. We're going to do that. In order to do that, though, we're going to look at pointers to a function. A pointer to a function contains the memory address of the function in memory. In Chapter 6, we saw that an array name is really the address in memory of the first element of the array. Similar, a function name is really the starting address in memory of the code that performs the function's task. Pointers to a function can be passed to functions, returned from functions, stored in arrays, or assigned to other function pointers. So we're going to take a look at a program that presents a modified version of the bubble sort. That the new version consists of a main method and a bubble, a swap, ascend, and descend. And the function bubble sort receives a pointer to a function, either ascending or descending as an argument, and then in addition to the integer array and size of the integer. And so the program prompts the user to choose whether the array should be sorted in ascending or descending order. If the user enters 1, the pointer to the function ascend is passed to the function bubble, causing the array to be sorted in increasing order. If the user enters 2, the pointer to the function descending is passed to the function bubble, causing the array to be sorted in descending order. And the output of that program is available in the next figure. This is figure 726 in your book. Basically, we have a function called bubble, an integer. An integer array called work, the size of the array as size t. Then you'll notice we have an integer, a pointer called compare, and then int a, int b. Okay, you'll notice that matches the prototypes for both ascending and descending, minus the names. So that is how you create a pointer to a function. The parameters and return type have to match that of the function that you wish to point to. And so when we look in our code, we are creating an array A of size 10 with 10 integers. We are going to print those. We are going to ask the user whether they want the item sorted in ascending or descending order. If we want them in ascending, we're going to call bubble with a pointer to the ascending function. If we want it to be descending, we're going to pass in bubble with the pointer to the descending function, and then of course we're going to output the sorted array. If we look at the bubble sort program, you will see that in our function header we have integer pointer to compare, int a, int b. And so what we're doing is essentially we're calling that function by referencing that pointer and then supplying the required values. And depending on what that pointer returns, whether it returns 0 or 1 or true or false, will determine if the items are out of order and should be swapped. The swap essentially takes the first item, puts it in hold, takes the second item, takes the second argument, assigns it to the first, takes the second argument, and assigns the value of hold to it. Now, our functions here of ascending or descending take two integer values. They return an integer. Basically, determine whether the items are out of, basically what we're doing here is determining whether the items are out of order for ascending. So if we want ascending, B needs to be less than A. If we want descending, B needs to be greater than A. So that is how you would use that sort of multi-purpose sorting program. This idea has carried through other languages that have been created from C, but they've done it, I think, a little bit more elegantly than C has done it. I'm not a huge fan of passing pointers to functions into other functions. I think that it's a little obtuse. I do not believe that it adds any clarity or readability. However, it does add flexibility. I'm sure there are occasions where it is necessary, but I can think of about 4 or 5 better ways to do this without passing in a pointer to a function. Although, again, sometimes it is necessary, and it's definitely useful here. I can't say that it is not useful. It is definitely useful here. We can look at the output of the bubble sort program that we just looked at, both ascending and descending. So it's pretty cool how it works. Again, all it is switching the comparison, is switching whether or not the comparison should occur, given which function is passed into the bubble sort program. The parameter that appears in the bubble sort, this tells the bubble sort to expect a parameter compare that is a pointer to a function that receives two integer parameters and returns an integer result. So that's essentially what that is. The parentheses are needed around compare to group the star with the compare to indicate that compare is a pointer. If we had not done that in parentheses, the declaration would have been int star compare, and then two parameters in parentheses, which declares a function that receives two integers as a parameter and returns a pointer to an integer. And that wouldn't work for what we were trying to do. The third parameter in the prototype could have been written as int in parentheses star int without the function pointer name and without the parameter names. If the function is passed to the bubble sort, that function then is called in an if statement. If the pointer to the function name and then the values that we need, just as the pointer to the variable is dereferenced to access the value of the variable, the pointer to the function is dereferenced to call the function. The call to the function should have been made without dereferencing, could have been made without dereferencing the pointer, which uses the pointer directly as the function name. We prefer the first method of calling through the pointer because it explicitly illustrates that compare is a pointer to a function that is dereferenced rather than calling an actual function. The second version, the version that you're looking at on this slide, makes it look like compare is an actual function, which it is not. And that's going to be confusing to somebody who reads the code, who would like to see if the definition of the function compare, and then they're going to find it's never defined in the file. And so if you put the dereference operator up there, it just makes that bit explicit, which I think is a good thing. I think it's good to make that quite explicit. You can use function pointers to create a menu-driven system. That's really sort of a common use of functions in text-based menu systems. The user is prompted to enter a menu option 1 to 5 by typing the menu's item number. Each option is serviced by different functions, and the pointers to each function are stored in an array, and the user's choice is used as the index, which makes life a little bit easy. We're going to look at a kind of a generic example of that, of using an array of pointers to functions. We've got 3 functions, function 1, function 2, and function 3, that take integer arguments and return nothing. We're going to store those pointers in an array of functions called f. So let's take a look at that. So we've got 4 prototypes, 4 method prototypes, functions 1, 2, and 3. All take integers. So we're going to set up an array of functions that point to each function. They notice that we have void, because they all return void. Pointer asterisk f3 in parentheses, again indicating that there are 3 separate function pointers. All of those functions are going to return void, and they all take in an integer value. Okay. We're going to ask the user to enter a number between 0 and 2 with the number 3 to end. We're going to read in their choice. If while their choice is greater than or equal to 0 and less than 3, we are going to call the function that they have picked and then ask them to enter a number again. When they enter something that is not 0 to, that is not greater than or equal to 0 and less than 3, we are going to exit the program. If they enter 0, we're gonna call function 1. If they enter 1, we're gonna call function 2. If they enter 2, we're gonna call function 3. And you can see that here. And so that's kind of a generic way to do that sort of menu-driven system, which is actually, that is probably a really good use for an array of functions. It makes very quick access. You don't have to do a lot of if statements around, or a select case around what the user's choice was. So that's probably a decent option when to use pointers to functions. But again, generally, I'm not a big fan of them. We've looked at that. All right, so let's talk about secure programming. So printf_s, scanf_s, and other secure functions. The key feature of printf_s and scanf_s that makes them more secure is that they have runtime constraints requiring that their pointer arguments be non-null. The functions check the runtime constraints before attempting to use the pointers, and any null pointer argument is considered to be a constraint violation, which causes the function to fail and returns a status notification. Now, remember, not all platforms have printf_s or scanf_s or some of the other secure functions. If scanf_s, in scanf_s, if any of the pointer arguments, including the format control string, are null, the function returns end of file. In printf_s, if the format control string or any of the arguments that correspond to %s are null, the function stops outputting data and returns a negative number. So those are some things to think about when using those, and why it's a good idea to use them, and what to expect if you have pointers to null data. For other CERT guidelines regarding pointers, misused pointers lead to many of the most common security vulnerabilities today. Like I said, pointers are very powerful, and with great power comes great responsibility. CERT provides some guidelines to help you prevent problems. If you're building industrial strength C systems, you really need to familiarize yourself with the secure coding standards. We're going to look at some guidelines that apply to pointer techniques that we've presented so far. So first of all, in EXP 34-C, dereferencing null pointers cause programs to crash generally, but CERT has encountered cases where dereferencing null pointers will allow attackers to execute code. Again, that depends on the implementation of the C compiler, but you do need to be aware of it. DLC 13-C in section 7.5 of the book discusses the use of constant with pointers. If a function parameter points to a value that will not be changed by the function, the const keyword should be used to indicate that the data is constant, so that it doesn't get modified. Again, while not necessarily well implemented on every system, it is important to do this because it is just one extra tool in the security belt to make sure that attackers can't change your data. MSC 16-C is a guideline that discusses techniques for encrypting function pointers to prevent attackers from overwriting them and then executing code. So all things that you need to think about. So that's it for our discussion of pointers. You'll have some code labs to go through, and then you can take a look at your reading and your quiz and your programming assignment for this week. If you have any questions, please let me know. bsimbeck@ccac.edu. Pointers are probably the hardest thing about C because all of the more modern object-oriented languages got rid of pointers because of a lot of the dangers that we just talked about. And so in more modern object-oriented languages, pointers are kind of gone. And so we don't use them very much anymore. Unless you're really in hardcore C or hardcore C++, you're not really using pointers anymore. And again, it's because of the dangers that are associated with pointers, the problems that can come up with pointers that are the reason why we do that. But they're still important to know because they are a building block in how we got to where we are today. And so we need to be aware of them. If you have any questions about this or anything that we've talked about, please email me, bsimbeck@ccac.edu. I'd love to hear from you. Come see me during office hours, 6:30 to 7:30 on Thursday nights at South Campus B609. If you need help and you can't get to me, feel free to check in with the tutor. I know we're starting to get into some hot and heavy material. And some complicated material, but it's important to know. And so if you need help, let me know, or go see a tutor. Please don't delay. Have a great week, everybody, and let me know if you have any questions.